November 8, 1943, Sicily. An LST designated number 325 drove itself onto a beach near Gela at 8 knots, ploughing through shallow water until its flat bow scraped onto sand. The ship, weighing 4,800 tons, fully loaded, shuddered as its momentum died. Then something happened that would have seemed like engineering fiction just 2 years earlier. The massive bow doors swung open. A ramp extended forward, and 20 Sherman tanks, each weighing 33 tons, rolled directly onto dry beach in 14 minutes and 42 seconds. Standing on that beach was a British tank officer named James Holworth, whose unit had spent 6 hours the previous day attempting to unload 8 Churchill tanks using conventional methods: cranes, smaller landing craft, improvised ramps. His diary entry, preserved in the Imperial War Museum archives, captured the moment with understated British shock. The Americans have built a ship that beaches itself like a whale and vomits tanks as though they weigh nothing. Watched an entire armoured company drive off one vessel before I finished my tea. Our landing officers stood speechless. The mathematical impossibility of it all. That mathematical impossibility represented a revolution in naval warfare that experts had declared could never happen. Ships don't beach themselves. Everyone in the maritime world knew this fundamental truth. A vessel deliberately driven aground becomes trapped, vulnerable, useless. Naval architecture textbooks going back 3 centuries explained in meticulous detail why large ships required deep water, protected harbours, and extensive port facilities. The physics were immutable. The engineering was settled science. And then the United States built 883 ships specifically designed to violate every principle those textbooks considered sacred. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis began in June 1942, 6 months after Pearl Harbor, when Allied planners started seriously examining how to invade German-occupied Europe. The strategic requirement was brutal in its simplicity. They needed to land hundreds of thousands of troops, thousands of vehicles, and millions of tons of supplies across hostile beaches where German forces controlled every port facility from Norway to Spain. Traditional naval doctrine provided no solution. Armies required ports. Mechanized warfare demanded heavy equipment that couldn't be carried in small boats. Every military operation in history had depended on capturing harbour facilities to enable supply lines, but every useful port in Europe was now heavily fortified, rigged with demolition charges, defended by coastal artillery that could sink transport ships before they reached unloading range. The British had learned this lesson catastrophically at Dieppe in August 1942. Canadian forces attempted a raid on the French port, and German defenders slaughtered them. Of 6,000 men landed, only 2,400 returned. The survivors reported that German coastal defences made port facilities death traps. Any frontal assault on a functioning harbour would result in casualties that would make victory meaningless. American planners faced the same math from a different angle. The Pacific Island hopping campaign required taking islands that had no ports at all. Just coral reefs, volcanic beaches, and Japanese defenders who controlled every inch of shoreline. Douglas MacArthur's staff calculated that using conventional amphibious methods, taking islands like Tarawa or Saipan would require landing supplies for weeks through small craft shuttling from transport ships to beaches. The logistical bottleneck would be absolute. Admiral Ernest King, Commander-in-Chief of the United States Fleet, summarized the problem in a memorandum dated July 19, 1942. We must deliver Army-level forces across open beaches without port facilities. Current capabilities insufficient by factor of 10. Require vessel capable of delivering heavy equipment directly to shore in quantity. No such vessel exists or can exist under known naval architecture principles. That final sentence, "No such vessel can exist," represented conventional wisdom accumulated across centuries of maritime engineering. Ships were built for deep water, beaches destroyed ships. The two concepts were fundamentally incompatible. The initial specifications that the Navy Bureau of Ships circulated to American shipyards in August 1942 read like a list of contradictions. They needed a vessel that could carry 20 tanks or 40 trucks, cross oceans in convoy with deep-water cargo ships, approach to within touching distance of a beach, unload its entire cargo directly onto sand, then extract itself and return for another load. The draft couldn't exceed 3 feet at the bow when unloading, but the ship needed stability for ocean crossings. It required bow doors large enough to drive a tank through, but those doors had to withstand Atlantic waves during the voyage. Most damningly, the whole package needed to be simple enough that shipyards could build them by the hundreds using semi-skilled labor. John Niedermeyer, chief naval architect at Newport News Shipbuilding, one of America's most prestigious yards, wrote a response that the National Archives preserved in procurement files. The specifications describe a vessel that cannot float, cannot beach without breaking its back, and cannot extract itself even if it somehow survived beaching. The Bureau requests a ship that violates hydrostatic principles, structural engineering limits, and basic physics. Respectfully suggest specifications be revised by persons with maritime training. But the Bureau of Ships wasn't staffed by amateurs. Rear Admiral Edward Cochrane, chief of the Bureau, held degrees from both the Naval Academy and MIT. His staff included some of the brightest naval architects in America. They knew the design seemed impossible. They also knew that impossible was the only option that led to victory. The solution emerged from an unlikely source. The British, despite their conservative naval traditions, had been experimenting desperately with shallow draft landing ships since Dunkirk. In 1940, watching their army evacuate France in fishing boats and pleasure craft, British planners recognized they'd eventually need to invade back across the English Channel. They started designing specialized vessels immediately. The British motor landing craft, developed in 1941, featured a flat bottom and bow doors. It could carry 3 tanks and beach in shallow water. But the design had crippling limitations. The vessel was small, just 60 feet long, unstable in rough seas, and its construction required specialized shipyard techniques that couldn't scale to mass production. The British built approximately 860 of them by the war's end, each one taking skilled craftsmen about 8 weeks to complete. What the Americans needed was something far more radical, not a large landing craft, but a true ocean-going ship that could beach itself. The conceptual leap required abandoning nearly every assumption that defined what a ship was supposed to be. The breakthrough came from a British design that never worked properly. In 1940, the Royal Navy experimented with shallow draft vessels called Atlantic Tank Landing Craft, intended to carry heavy armor across the English Channel. The design featured a flat bottom, ballast tanks that could be flooded to adjust draft, and primitive bow doors. But the British version had fatal flaws. The hull flexed and cracked under stress. The bow doors leaked constantly. The ballast system was so complex that crews needed days of training just to understand the pumping sequences. The British sent the plans to America in early 1942 as part of war material sharing agreements. American naval architects examined them and saw both the promise and the problems. The key insight came from a design team at the Bureau of Ships led by Commander John Crommelin Blue. Blue had spent the 1930s working on cargo ship designs and understood structural engineering from a commercial rather than military perspective. Looking at the British plans, he recognized that they'd approached the problem backwards. The British had started with a conventional ship hull and tried to modify it to beach. Blue proposed starting with a barge and making it seaworthy instead. A barge doesn't care about hydrodynamic efficiency. It's a floating box designed to carry maximum cargo with minimum draft. Barges beach routinely, although they don't usually extract themselves. Blue's concept was to take barge-like proportions, add enough propulsion to drive the vessel at 10 knots, incorporate ballast tanks that could pump water out rapidly to reduce draft for beaching, and design structural strength to handle the stresses of grounding. The revolutionary part was the ballast system integration. Blue proposed massive tanks running the length of the ship that could be flooded during ocean transit to add stability and lowered draft for beaching by pumping out millions of gallons in minutes. The mathematics suggested it could work. The engineering would be extraordinarily complex. Admiral Cochrane brought the concept to the Preliminary Design Review Board in October 1942. The board, composed of senior naval architects and experienced ship captains, spent 3 days analyzing Blue's proposal. Their collective skepticism filled 27 pages of meeting minutes. Captain Harold Smedberg, a naval architect with 30 years of ship design experience, summarized the technical objections. A flat-bottomed vessel of this size will pound itself apart in moderate seas. The proposed ballast system requires pumping capacity beyond any merchant vessel ever built. The structural stress of beaching a 4,000-ton ship will crack the keel within weeks. The bow door mechanism cannot possibly withstand wave forces during ocean crossing. This design represents not innovation but maritime suicide. Yet, Admiral Cochrane pushed forward, driven by desperate necessity. The final approval came with a caveat that revealed how uncertain the Navy remained. They would authorize construction of a trial vessel, but not commit to mass production until that prototype proved seaworthy and demonstrated the ability to beach and retract successfully at least 20 times. The contract went to Dravo Corporation in Pittsburgh, Pennsylvania. This choice itself was revealing. Dravo didn't build ships, they built river barges, which was exactly the point. The company's expertise in flat-bottomed vessels that could ground safely made them ideal for this unconventional design. The first LST, originally designated landing ship tank but quickly nicknamed Large Slow Target by sailors who would eventually crew them, started construction in June 1942. The vessel measured 328 feet long, 50 feet wide, and when fully loaded drew just 3 feet 9 inches forward, 11 feet aft. Those proportions were absurd by conventional ship standards. Normal cargo vessels might have a length-to-beam ratio of 7 or 8 to 1. The LST was 6.5 to 1, making it proportionally wider than any ocean-going vessel in service. The hull shape horrified traditional ship designers. Instead of a sleek bow cutting through water, the LST's front end was flat, almost perpendicular to the waterline, like a barn door. This created enormous resistance during ocean transit, limiting the ship to a maximum speed of about 11 knots in ideal conditions and often significantly slower in rough seas. But that flat bow was essential for beaching. It distributed weight across maximum surface area when the ship grounded. The ballast tank system was the real engineering marvel. 4 tanks, each holding thousands of gallons of seawater, ran along both sides of the ship. During ocean crossing, these tanks stayed flooded, adding weight that lowered the vessel deeper in water, improving stability in heavy seas. When approaching a beach, pumps could empty all tanks in approximately 20 minutes, raising the bow to reduce draft from 8 feet to under 4 feet. This system required pump capacity that dwarfed normal maritime standards. The LST-1, the prototype, carried 6 main ballast pumps, each capable of moving 2,000 gallons per minute. The power requirements were staggering, consuming electricity that a normal cargo ship would dedicate to auxiliary functions. The bow door mechanism represented the design's most vulnerable point. 2 massive clamshell doors, each weighing several tons, met at the centerline. When closed, they formed the ship's bow, supposedly watertight enough to survive Atlantic storms. When opened, they swung outward to reveal a ramp that lowered to the beach. The hinges, latches, and sealing system had to handle forces that could rip apart conventional doors within hours. Dravo's engineers designed the system with brutal simplicity. The hinges were massive steel pins 8 inches in diameter. The latches used redundant manual and hydraulic systems. The sealing employed rubber gaskets 3 inches thick, backed by mechanical pressure systems that could be tightened manually if hydraulics failed. Every component was overbuilt to ridiculous specifications because the designers knew the consequences of failure would be catastrophic. LST-1, launched in October 1942. The vessel immediately proved that skeptics had been partially right. It was slow, uncomfortable, and handled like a drunken barge in anything rougher than calm seas. Sailors reported that the flat bottom made the ship pound through waves rather than riding over them, creating a motion so violent that seasickness became universal. Crew quarters felt like being inside a drum while someone beat it with hammers. But when LST-1 conducted beaching trials in Chesapeake Bay in November 1942, something remarkable happened. The ship approached the beach at 6 knots, drove its bow onto sand, pumped out ballast tanks, opened bow doors, extended the ramp, and sat there in 3 feet of water while trucks drove directly off onto the beach. Then came the moment that would determine whether the entire concept was viable or fantasy. The crew closed the doors, flooded ballast tanks to lower the stern and raise the bow, and engaged the propellers in reverse. The ship shuddered, shifted, and slowly backed off the beach into deeper water, extracting itself exactly as designed. The naval observers present included 3 admirals who had voted against the project initially. Their reaction, documented in official trial reports, showed the psychological impact of seeing theoretical engineering become physical reality. Admiral Frederick Horn wrote, "Observed LST, 1 complete full beach cycle, including unloading and extraction. Vessel performed as specifications claimed. Must revise assumptions regarding large vessel beach operations. Recommend immediate mass production." That single successful demonstration in Chesapeake Bay in November 1942 triggered a procurement order that would transform American amphibious capabilities. The Navy authorized construction of over 200 LSTs immediately, with contracts distributed to shipyards across the country, many of which had never built ocean-going vessels before. The production challenge made Liberty ships look simple by comparison. An LST contained approximately 400 tons of steel, 2 diesel engines, 6 main pumps, electrical systems throughout, and that complex bow door mechanism. Traditional shipyards estimated 18 months to build such a vessel. The Navy demanded delivery in 6 months at a rate that would eventually reach dozens of ships monthly. The solution borrowed directly from Henry Kaiser's Liberty ship revolution: prefabrication, welding instead of riveting, assembly line techniques, and mass training of unskilled workers. But LST construction added complications that Liberty ships didn't face. The ballast system's precise tolerances made welding quality absolutely critical. A leak in a ballast tank could mean the difference between successful beaching and drowning the vehicle deck. The shipyards that received LST contracts in late 1942 faced an immediate crisis. None of them had built anything remotely similar. The Chicago Bridge and Iron Company in Seneca, Illinois, normally fabricated industrial storage tanks. Dravo Corporation built river barges. American Bridge Company constructed, bridges. Yet these firms were suddenly expected to produce ocean-going assault ships capable of surviving Atlantic crossings and deliberate groundings. The Navy's training approach revealed how desperate the situation was. They sent experienced LST-1 crew members to each new shipyard for 2-week instruction courses. These sailors, who'd spent maybe 3 months total aboard the prototype, were now teaching shipyard workers how to build systems they'd barely mastered themselves. It was the maritime equivalent of having flight students teach aircraft design. But the approach worked because the LST design, despite its sophistication, was fundamentally modular. The ship broke down into major sections that could be fabricated separately by crews who specialized in specific tasks. One team built hull sections, another assembled the bow door mechanism, a third fabricated ballast tanks. Final assembly brought the pieces together. Jefferson City, Missouri, 1,500 miles from the nearest ocean, became a major LST production center. The facility sat on the Missouri River, with sufficient water depth to launch completed vessels. Workers who'd never seen a ship larger than a fishing boat learned to weld hull plates and install pumping systems. By mid-1943, the Jefferson City Yard was delivering 2 LSTs monthly. The workforce transformation mirrored what happened in Kaiser's Liberty shipyards. Women comprised approximately 30% of LST construction workers by 1944. The welding positions, absolutely critical given the ballast system's requirements, were often filled by women who'd learned the skill in 3-week training courses. Quality control inspectors reported that welds performed by properly trained women failed at rates statistically identical to those performed by experienced male welders. Chicago Bridge and Iron employed a particularly elegant solution to the complexity problem. They built a full-scale wooden mock-up of an LST's interior before constructing any actual ships. Workers practiced installing pumps, routing electrical lines, and fitting ballast tank components in this three-dimensional template. By the time they worked on real vessels, muscle memory had already solved most assembly challenges. Construction time dropped from 9 months for their first ship to 4 months by their fifth. The ballast tank fabrication revealed why the LST design pushed manufacturing capabilities to their limits. Each tank had to be absolutely watertight, hold pressure when flooded, and withstand the shock of beaching that could slam thousands of gallons of water against interior walls with tremendous force. The welding specifications called for X-ray inspection of critical seams, a quality control measure that was cutting edge for 1943 industrial production. One particular failure mode haunted early LST operations. If ballast tanks weren't completely sealed, slow leaks could flood them during ocean crossing. The crew might not notice until they attempted to pump out for beaching and discovered the pumps couldn't overcome the leak rate. The ship would sit offshore, too deep to beach properly, with tanks that couldn't be emptied. This happened to LST-69 during trials in March 1943. The vessel had to return to the shipyard for 3 weeks of re-welding before becoming operational. After that incident, the Navy mandated pressure testing for every ballast tank before a ship could be commissioned. Workers would seal a tank, pump air pressure to 15 pounds per square inch above atmospheric, and monitor for 24 hours. Any pressure drop indicated leaks that required finding and repairing. This added a week to construction schedules, but eliminated catastrophic failures. By spring 1943, American shipyards were producing LSTs at a rate that seemed impossible to foreign observers. Monthly production reached 20 vessels in April, 32 in May, and peaked at 38 in June. The British, who'd struggled to build their smaller tank landing craft, watched American mass production with the same mixture of admiration and disbelief they'd felt watching Liberty ship construction. A British liaison officer stationed at the Charleston Navy Yard wrote in his April 1943 report to the Admiralty, "The Americans build LSTs the way we build lorries. Standardized components, interchangeable parts, workers who learned their trades in weeks rather than years. The results are crude by Royal Navy standards. These ships pound through seas rather than riding them properly. But they work, they're seaworthy, and there are dozens of them appearing monthly." The first combat test came on July 10, 1943, Operation Husky, the invasion of Sicily. 169 LSTs participated in the initial landings, carrying approximately 4,000 vehicles, including tanks, trucks, artillery pieces, and jeeps, directly to Sicilian beaches. The operation revealed both the LST's revolutionary capabilities and its practical limitations. At Gala, where American forces landed, LSTs drove themselves onto beaches in waves. Each ship grounded, opened bow doors, and began unloading. The process that had taken 14 minutes in training took significantly longer under combat conditions because tanks had to wait for sappers to check for mines. Traffic jams developed on the beach as vehicles concentrated in limited cleared areas, and German artillery forced ships to occasionally close doors and wait out bombardments. But even with these complications, the efficiency was staggering compared to any previous amphibious operation. Lieutenant Harold Morrison, a logistics officer with the 1st Infantry Division, watched the landings from the beach and recorded his observations. LSTs grounded approximately every 8 minutes during the first 4 hours. Each ship carried either 20 tanks or 40 trucks. By noon, we'd landed over 300 vehicles at this single beach. The mathematics of it seemed absurd. Historically, landing that much heavy equipment required capturing a port facility. Now we're creating an artificial port simply by throwing ships at the beach repeatedly. The German response revealed how completely the LST changed defensive calculations. German coastal defense doctrine assumed that Allies needed ports and that destroying port facilities would cripple any invasion. At Sicily, German engineers had prepared demolitions for every harbour. They'd mined the approaches, pre-registered artillery on dock areas, and positioned the best troops to defend ports. But the Americans didn't need the ports. They drove LSTs onto open beaches and unloaded entire armoured divisions, while German forces watched in confusion. Italian prisoners captured at Gela reported that German officers kept asking when the real invasion would come, the one targeting the ports, because surely the beach landings were just a diversion. One particular incident at Gela demonstrated the LST's combat resilience. LST 313 was grounded and unloading when German artillery found the range. A shell penetrated the starboard bow door, exploding inside the tank deck. The blast killed 3 sailors and damaged the door mechanism. By conventional wisdom, the ship was done. A crippled vessel grounded on an enemy beach becomes an easy target. The crew improvised. They couldn't close the damaged starboard door, but the port door was functional. They shifted ballast to list the ship slightly to port, using the intact door as partial protection. They continued unloading tanks, which had to navigate around the blast damage. Once empty, they flooded ballast tanks asymmetrically to compensate for the list, gunned the engines, and extracted themselves. The ship made it back to North Africa under its own power, took temporary repairs, and was operational again within 6 days. That resilience, the ability to absorb damage and keep functioning, became a defining characteristic of LST operations. The ships weren't elegant, they weren't fast, but they were extraordinarily tough to kill completely because their simple, overbuilt construction had few critical single points of failure. Salerno, in September 1943, provided the next test. The landing faced stronger German resistance than Sicily, and LSTs operated under sustained counterattack for days. German dive bombers targeted the ships specifically, recognizing them as the source of Allied armoured strength. LST 357 took a bomb hit that blew a 15-foot hole in the tank deck. The crew patched it with welded steel plates and timber shoring while still grounded on the beach, continued unloading, then successfully extracted and made it to a repair ship. The psychological impact on German commanders was profound. Field Marshal Kesselring, commanding German forces in Italy, sent a situation report to Berlin in late September 1943 that intelligence officers intercepted and decrypted. His assessment was brutally honest. American landing ships eliminate our coastal defense advantage. They deliver armored forces directly to beaches without requiring port facilities. We cannot defend everywhere. Enemy can choose landing sites almost at will. Our strategy of port denial has become irrelevant. The Pacific Theater provided an even more dramatic demonstration of LST capabilities. Coral reefs that had protected Japanese-held islands for centuries became merely inconvenient obstacles. At Tarawa in November 1943, larger landing ships grounded on reefs far from shore, but LSTs drew shallow enough to cross the reefs, delivering tanks and artillery directly to beaches, while Japanese defenders watched in disbelief. Admiral Raymond Spruance, commanding the Fifth Fleet during the Gilbert Islands campaign, sent an assessment to Admiral Nimitz that captured the strategic revolution. LSTs have transformed Pacific operations from problematic to routine. Islands previously considered impossible to assault due to reef systems are now accessible. Japanese defensive calculations assumed we'd need to capture ports to sustain operations. LSTs allow us to establish supply lines across any beach with sufficient gradient. Enemy must now defend every island's entire perimeter rather than concentrating forces at harbours. Now let's examine the mechanical choreography that made LST operations work. The claim that crews could unload 20 Sherman tanks in 15 minutes sounds like propaganda exaggeration. It wasn't. Here's how the system functioned in practice. The approach began 2 miles offshore. The ship's navigator and beachmaster, an officer who'd memorized tidal charts and beach gradients for the specific landing site, would calculate the optimal approach time. They wanted to beach at or just after high tide, giving maximum time to unload before the tide fell and potentially trapped the ship. As the LST closed to within a quarter mile, the engineering crew began pumping ballast. The massive pumps, 6 of them running simultaneously, moved water at extraordinary rates. Each pump displaced 2,000 gallons per minute. Running all 6 pumps meant emptying 12,000 gallons every 60 seconds. The forward ballast tanks held approximately 180,000 gallons total. Do that arithmetic, and you get 15 minutes of pumping to completely empty forward tanks. But the crew didn't wait for complete emptying. They pumped enough to reduce bow draft to approximately 4 feet, which took about 8 minutes, then maintained that level as they approached. The ship's captain aimed for a specific beach location, typically marked by coloured smoke or flags planted by reconnaissance teams. As the flat bow contacted sand, the ship's momentum drove it forward and slightly upward. The sensation, reported by crew members across dozens of interviews, was like hitting a massive speed bump at moderate velocity. The entire ship shuddered. Equipment not properly secured slid forward. Then, stillness as grounding stopped all forward motion. Immediately, 3 critical actions happened simultaneously. First, the engineering crew shifted pumping from maintained level to maximum emptying, pulling every remaining gallon from forward ballast tanks to lift the bow as high as possible. Second, the deck crew activated the bow door mechanisms. 2 sailors operated hydraulic controls while 2 more stood ready with manual backup systems in case hydraulics failed. Third, the tank commanders inside the cargo deck started their engines. The bow doors, each weighing approximately 8 tons, swung outward on those massive 8-inch steel hinges. The hydraulic cylinders that moved them were powerful enough to operate even with the ship listing at angles up to 10 degrees. Opening time was approximately 45 seconds under normal conditions. Once doors were fully open, sailors activated the ramp extension mechanism. This was a separate steel ramp, 40 feet long and weighing 3 tons, that extended forward from the ship's bow to bridge the gap between ship and beach. In ideal conditions with proper tidal calculations, the ramp touched dry sand. In rougher conditions or poor tidal timing, the ramp might terminate in 6 inches of water, which tanks could handle easily. Now the tanks began moving. Sherman tanks in 1943 weighed approximately 33 tons combat loaded. They could drive at perhaps 3 miles per hour in first gear, which translated to about 4.4 feet per second. A Sherman was roughly 20 feet long from bow to stern. An LST's tank deck measured roughly 290 feet long and 30 feet wide. Tanks were loaded in 2 rows, 10 tanks per row typically, parked nose to tail with minimal spacing. The unloading choreography was carefully rehearsed. Right row went first. Tank commanders would start engines, shift into gear, and follow painted lines on the deck. The lead tank would roll down the ramp, turn right on the beach to clear space, and move inland to the designated assembly area. Second tank would follow 15 seconds later, turn left to avoid the first tank's path. This alternating pattern continued. Right row, left row, right row, left row. Each tank cleared the ramp in approximately 8 to 10 seconds of drive time. Add the 15-second interval to allow adequate separation, and you're launching 1 tank roughly every 23 seconds. 20 tanks at 23 seconds each equals 460 seconds or 7 minutes, 40 seconds of pure driving time. But that calculation ignores the inevitable minor delays. A tank might hesitate confirming the path is clear. The ramp might need quick adjustment if the ship settles slightly as weight shifts. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Factor in realistic delays and coordination issues, and 15 minutes to fully unload becomes not just believable, but actually quite efficient. Training exercises logged unloading times between 13 and 18 minutes, depending on crew experience and conditions. Combat operations typically ran longer, 18 to 25 minutes, because combat introduces additional caution and potential interruptions from enemy fire. But even 20 minutes to unload an entire armoured platoon directly onto a hostile beach represented a capability that had never existed before. Traditional methods required cranes to lift vehicles into smaller landing craft, which then shuttled to shore. That process took hours for equivalent cargo. The extraction phase was equally impressive mechanically. Once empty, the LST's total weight dropped by approximately 700 tons, the combined mass of 20 Sherman tanks. This dramatic weight reduction meant the ship's draft decreased naturally as it rode higher in water. The crew would close bow doors, a 90-second operation, then immediately begin flooding after ballast tanks. These tanks, located near the stern, held approximately 200,000 gallons. Filling them caused the ship's stern to settle deeper into water, while the bow, now lighter and with emptied forward ballast tanks, rose higher. This differential ballasting created a pivot effect. The ship's stern dug deeper, the bow lifted, and the entire vessel essentially tilted backward. Combined with full reverse throttle on both main engines, this configuration allowed the ship to slide backward off the beach. The engineering was more art than science. Too much flooding aft and the stern might bottom out on submerged obstacles. Too little and the bow remained stuck. Experienced LST captains developed an intuitive feel for the correct balance, adjusting pump rates based on how the ship responded. Extraction typically took 3 to 5 minutes from door closing to reaching water deep enough for maneuvering. Some crews achieved it in under 3 minutes in optimal conditions. The record, according to Navy operational logs, was LST-47 at Empress Augusta Bay in November 1943, which extracted in 2 minutes, 18 seconds after unloading under heavy Japanese artillery fire. Motivation apparently improved efficiency. Now multiply this capability across dozens of ships operating in coordinated waves, and you understand how LSTs transformed amphibious warfare. At Normandy on June 6, 1944, LSTs delivered the entire armoured component of the invasion's initial waves. While Hollywood focuses on infantry storming Omaha Beach, the mechanized breakthrough that allowed forces to push inland came from LST's landing tanks directly onto Utah and Gold and Juno beaches throughout the day. The operational statistics from Normandy revealed the scale. 236 LSTs participated in the initial D-Day assault. Each made an average of 2 beach runs during the first 24 hours. That's 472 individual beaching operations, delivering approximately 9,400 vehicles to French beaches in one day. The German defenders had prepared for an amphibious invasion, but their defensive calculations assumed the Allies would need days to establish armoured strength ashore. German intelligence estimated that landing significant tank forces would require either capturing Cherbourg harbour or building elaborate temporary port facilities. Neither seemed immediately feasible. Instead, by nightfall on June 6th, Allied forces had more operational tanks on French soil than the German defenders had available to counterattack. The strategic surprise wasn't the invasion itself, but the speed at which Allied forces transitioned from beach landing to armoured offensive. Field Marshal Rommel, inspecting coastal defences in May 1944, had told subordinates that the invasion must be defeated on the beaches within the first 48 hours, or Germany would lack sufficient reserves to contain the breakthrough. The LST's ability to rapidly deploy armour made Rommel's 48-hour window effectively meaningless. By hour 48, Allied forces were already 30 miles inland with supply lines functioning. Japanese commanders in the Pacific experienced similar shock. At Saipan in June 1944, Japanese defenders had built elaborate beach fortifications, assuming they'd have time to counterattack, while Americans struggled to land heavy equipment. Instead, LSTs drove onto beaches and within hours, American forces had dozens of tanks and mobile artillery pushing inland. The Japanese defensive plan, built around destroying isolated American units before they could concentrate, collapsed because concentration happened faster than Japanese doctrine considered possible. The human cost of LST operations deserves recognition. These ships weren't safe. Their slow speed and predictable approach patterns made them targets. German and Japanese forces quickly learned to concentrate fire on LSTs, recognizing them as high-value targets. 66 LSTs were sunk or destroyed during the war. Another 226 suffered significant damage requiring major repairs. Crews serving on LSTs faced approximately a 12% chance of their ship being hit seriously enough to cause casualties during combat operations. LST 531 sank during D-Day rehearsals in April 1944 when German torpedo boats attacked the convoy. 441 soldiers and sailors died. LST 282 took a kamikaze hit at Okinawa in April 1945, killing 38 crew members and 23 Army personnel waiting to unload, but the LST's damage resilience meant that ships hit often survived. The compartmentalized design, with watertight bulkheads throughout, meant flooding could be contained. The redundant systems, manual backups for hydraulics, multiple pumps for ballasting, meant damaged ships could often complete their mission even after taking hits that would cripple conventional vessels. LST 538 at Anzio in January 1944 took 3 shell hits from German coastal artillery. One penetrated the starboard side, flooding a ballast tank. Another hit the superstructure, destroying radar and communications. The third struck the bow door mechanism, jamming the starboard door. The crew opened the port door only, unloaded tanks, and extracted successfully. The ship remained operational with temporary repairs for 6 more months before returning to the United States for full refit. The longevity of LSTs proved skeptics wrong about structural durability. Naval architects had predicted the stresses of repeated beaching would crack keels and break welds within months. Many LSTs served continuously for 2 to 3 years, making dozens of combat beachings without catastrophic structural failure. LST 325, commissioned in February 1943, participated in the Sicily invasion, Salerno landing, Normandy invasion, and southern France campaign. It made approximately 60 confirmed combat beach landings before the war ended. The ship survived and remained in service with the U.S. Navy until 1947, then served in the Greek Navy until 1999. In 2000, American veterans groups purchased it, sailed it across the Atlantic under its own power at age 57, and it now serves as a museum ship in Evansville, Indiana, still capable of beaching operations. The post-war influence of LST design principles extended far beyond the vessels themselves. The concept of ships deliberately designed to beach and unload directly became fundamental to amphibious warfare doctrine. Every modern navy with amphibious capabilities operates descendants of the LST. The United States Navy's current Newport-class LSTs, commissioned in the 1960s and 70s, used refined versions of the same basic design, larger, faster, more sophisticated, but still fundamentally a ship with a flat bottom, bow doors, and ballast systems designed for deliberate beaching. These vessels served through the Gulf War in 1991, making beach landings in Kuwait using principles developed 50 years earlier. The Chinese People's Liberation Army Navy studied American LST operations extensively when developing their Type 071 amphibious transport dock. While more advanced than World War II designs, the operational concept remains identical. Deliver heavy armor and vehicles directly to hostile beaches without requiring port facilities. Modern amphibious warfare training at bases like Camp Pendleton still teaches the choreography of LST-style operations. Officers learn tidal calculations, beach gradient assessment, ballast management timing. The technology has improved, but the fundamental mission hasn't changed. The strategic impact of LSTs on World War II's outcome is difficult to overstate. They enabled operations that would have been impossible or prohibitively costly otherwise. The island-hopping campaign across the Pacific relied completely on LST capabilities. Each captured island became a forward base because LSTs could deliver the construction equipment, vehicles, and supplies needed to build airfields and support facilities on beaches with no port infrastructure. In Europe, the rapid advance following Normandy happened because LSTs maintained supply lines even as Allied forces outran captured ports. Cherbourg, the nearest major port to the invasion beaches, wasn't captured until June 26, 3 weeks after D-Day. But Allied forces had already pushed deep into France because LSTs continued delivering supplies across the beaches. The production statistics tell their own story about American industrial capability. 883 LSTs, built between 1942 and 1945. That's approximately one ship every 2.5 days for 3 years. The peak production month was August 1943, when 62 LSTs were delivered. The workforce required for this production exceeded 100,000 people across dozens of shipyards. Women comprised roughly 40% of LST construction workers by 1944. African American workers held skilled positions, including welding, electrical work, and quality inspection, at rates unusual for that era. The economic impact extended beyond the ships themselves. Each LST required 2,000 horsepower diesel engines, typically built by General Motors or Fairbanks Morse. The pump systems came from specialized manufacturers in cities like Milwaukee and Cleveland. Steel came from mills in Pittsburgh, Gary, and Birmingham. The production created supply chains that employed tens of thousands of workers in supporting industries. The cost per ship provides context for the industrial commitment. An LST in 1943 cost approximately $1.5 million to build. 883 ships at that price equals roughly $1.3 billion total, approximately $19 billion in 2024 currency, accounting for inflation. For comparison, modern amphibious assault ships like the America class cost approximately $3 billion each in current dollars. The LST was crude but cheap, which allowed mass production that sophisticated designs couldn't match. The British operated 80 LSTs provided through Lend-Lease, and their experience offered external validation of the design. Royal Navy officers, initially skeptical of American maritime engineering, became converts after operating the vessels in combat. A British after-action report from Operation Overlord, the Normandy invasion, noted, "American LSTs proved unexpectedly seaworthy and reliable. The crude appearance masks engineering well suited to purpose. These vessels accomplish tasks no traditional ship can perform. The Royal Navy should adopt similar designs for future operations." Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The story of LST development ultimately represents a triumph of pragmatic engineering over conventional wisdom. Every expert in 1942 knew that large ships couldn't deliberately beach themselves. The physics were wrong. The engineering was impossible. The concept violated centuries of maritime practice. Then, American designers ignored what everyone knew and built ships that did it anyway. They succeeded because they abandoned assumptions about what ships should be and focused entirely on what this specific mission required. Speed didn't matter. Elegance didn't matter. Conforming to traditional hull shapes didn't matter. Only one thing mattered: getting tanks onto hostile beaches quickly and reliably. The LST accomplished that mission through brute force engineering: massive pumps, overbuilt structures, redundant systems, and acceptance that the ships would be uncomfortable, slow, and ungainly. But those ungainly vessels changed warfare. Admiral Richmond Kelly Turner, who commanded amphibious operations in both Atlantic and Pacific theaters, wrote in his post-war memoir, "The LST made possible every major amphibious operation after 1943. Sicily, Salerno, Anzio, Normandy. Every Pacific island landing depended absolutely on these ships. Without them, we would have fought a completely different war, probably a longer one with far higher casualties. The LST wasn't the weapon that won the war, but it was the tool that delivered the weapons that won the war." That assessment from one of World War II's most experienced amphibious commanders captures the LST's true significance. Not a weapon, but an enabler, a solution to a problem that experts had declared unsolvable. The 883 LSTs, built between 1942 and 1945, carried more than just tanks and trucks. They carried proof that engineering limitations often exist in minds rather than physics. They demonstrated that solving seemingly impossible problems sometimes requires ignoring experts and building the impossible thing anyway to see if it works. When LST 325 sailed across the Atlantic in 2000 at age 57, covering the same route it had travelled during World War II. The voyage wasn't just nostalgia. It was a floating reminder that the ridiculous, impossible, never-work ship designed in 1942 was still functional 60 years later, still capable of beaching itself, still able to open those massive bow doors and drive vehicles directly onto sand. The engineers who designed the LST are gone now. The shipyard workers who built them have mostly passed. But the legacy endures every time a modern amphibious force practices beach landings, every time military planners calculate how to deliver armoured forces without capturing ports first, every time someone looks at conventional wisdom and asks whether impossible really means impossible or just means nobody's built it yet. That question, posed by desperate necessity in 1942 and answered by 883 ships that supposedly couldn't exist, remains relevant anywhere engineering challenges seem insurmountable. The LST proved that sometimes the solution to an impossible problem is building the thing everyone knows won't work and discovering that everyone was wrong. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.